All right, so we've had about a week's worth of classes. And now it's time to just take a moment, reflect. How you're feeling, how you doing, pushing you pretty hard so far. But what you want to really think about is the rate at which you're learning. You've had 4 days on a number of topics, and I think it usually takes about 4 days to get a handle on, a lot of skill concepts in math. Some take a lot longer, some take less time. But how can you accelerate the rate at which you're learning? We even talked about that a little bit the other day with the shape, concave up, acceleration. Right? Well, one way is to get some flashcards. So we got a little scrimmage coming up. You call it a test if you want. It's a final exam based on everything we've done to this point. The problems that you've just been introduced to and you've only had a day to work on. No, I'm not worried about whether you get those right or wrong. But I would like to see some of the things like writing the equational line and so on and so forth that we've done now for 4 or 5 days start to show up in the correct column. One of the reasons I don't want you doing homework at night is if you do something wrong, you're getting good at doing something wrong. So hence, we're just replaying the classwork. And if you're putting the time in and you're not on your phone, and you're actually watching the videos and pushing the space bar and trying the problems, even if you know how to do them, it's good practice to just do them again, because it really does change the mathematical thought process in the brain. And you get a little quicker, a little stronger with something, and then you can think a little bit more about, geez, where'd this come from? How'd this all come about? So flashcards. Okay, and what we're going to do with flashcards is probably just the 3 problems that gave you the most problems, most trouble on the scrimmage or the test, call it what you want. And that's coming up probably tomorrow or the next day. Get us started with a little baseline of keeping an eye on the rate at which you're learning. You'll write 3 flashcards and you'll show them to me the next day. On one side, you'll put the problem, and on the other, the solution. And you start a little library of what's been giving you trouble. And hopefully those flashcards go on the bottom of the pile in another week or 2. But the act of writing them, and it shows that you're trying to learn from your mistakes, which is really what this class is all about. All right, so we talked at the beginning of the term that language matters. And I've talked to a lot of students and asked them what's factoring mean. And, it's something they've been doing for 3 years. And lots of times you can't get a coherent answer. I'm not saying I got the best definition, but this is an example of factoring. So let's take a look at it. 2 plus 4 equals 2 times 1 plus 2. That's called factoring. Okay, what did I do? I took a sum and I wrote it as a product. I'd almost rather us always say that. And then maybe we'll say factor at some point. But you're going to hear from me, take a sum or a difference. It could have been a difference. Right? And take the sum or difference and write it as a product. And there's rules that govern it. It's not the first time you've heard the first rule. Hopefully what went right through your noggin from one ear to the other. Take out what's common. And then the next rule is keep going if you can. And the next rule is keep going if you can. And the next rule is keep going if you can. You get the idea, I guess. All right. It's kind of prime factoring, right? So I'll be saying, write this sum or this difference as a product. Right? Because you might not have known 2 minus 4, 1 minus 2, is 2. All right. So we can use that skill in a variety of places, and trust me, you will. All right, so language matters, quadratics. Fancy term for a rectangle. Okay, but historically, that's the way it's come down to us. So when I say quadratics, quad meaning 4, 4-sided Latin, right? Rectangle has 4 sides. Okay. Don't get scared by the term. We're looking at rectangles and what we can do with those relationships. And boy, imagine that. What we can do with those relationships is basically what algebra is built upon. and to a large degree, and so is calculus to a large degree. So we want to get into a little deeper understanding of the relationships of dimensions, geometric dimensions, and what happens and how we manipulate them to study the real world out there. All right, so worksheet, I've put a little money symbol next to a couple of problems, as in, I probably have to say something, little something new, you know, but built off of something we've already done. So look for those, and I might stop the class at some point. And then I think it's problem 34. There's some exponential work, and I'm going to do a little display, a little visual display to help maybe understand inverses a little better. So don't miss that. All right, but your job is to make sure that all the problems that we did today in class, if you didn't get to them, you got at least a look through this video. All right, I've got everything written down over here. So it shouldn't take me too long. I put that there so it's easy to see. And we'll get started. And I think I'm doing a little better job of capturing, yep, the screen in a good position. Yeah, repetition's my friend. Okay, I covered all of that. So let's have at it. So here's a difference. 100 minus 9. And I think we probably did this diagram in class today. And we said, work with the square roots. And so this difference of two squares, 10 plus 3, 10 minus 3. Okay, 13 times 7 is indeed 91. And so that's a special case. So what's a perfect square? Any exponent that you can divide by 2. Okay, that'll come into play in a little while. 125 minus 27. Never surprises me how long it takes students to memorize the pattern here. All right, I'm talking months. All right, some people do it in a day, 2 days, because they're actually giving it their mindful attention. And I just let the class continue. And 2 months later, oh, somebody else figured it out. All right, so cubes. Yeah, probably working with the cube roots, yes? Okay, so 5 minus 3. If it's a subtraction, it's a subtraction. Times what? First number squared. Well, yeah, that gives me 5 times 25. Great. The end has to get me negative 27. So that's got to be positive 9. Minus 3 times 9. Yes. Something here has to cancel out everything else. And it turns out that it's the opposite of this product. This product's minus 15. It becomes positive 15. Okay, and let's see where the cancellation takes place. I've got 5 times 15, which is 75. 5 times 15, 75. And minus 3 times 25 is minus 75. I've got 5 times 9 is 45. 5 times 9. I also have minus 3 times 15, which is minus 45. Well, there's the 4 things. 2 times 3 things is 6 things. 4 of them just canceled. 2 didn't. Okay, so there's a pattern. Now, if this had been a plus, that would have been a plus. That would have been a minus. All right. Been put in front of you. Let's see who's been doing their homework by actually watching this and thinking about it. All right, 9/8 to the 6th minus 4. Big clue here. Sure looks like 4 is a square. Look like 9 is a square. 3 times 3. And any even integer exponent can be expressed as a square. So what's this one? 3a to the 3 plus 2 times 3a to the 3 minus 2. And I got positive 2 of these, minus 2 of those. We can see the cancellation. And a to the 3 times a to the 3 is a to the 6th. That one is now done. All right, so what's a perfect cube? Any exponent that can be divided by 3. But right now we've got 27x cubed plus 125. And we have the sum of two cubes. We are now going to write it as a product. This can be written as, yep, I can put it there. The cube root of the first term, 3x, plus the cube root of the second term, 5. Now we build off of what's in this parentheses by squaring the first. Now I get that term when I multiply. Subtraction, we need cancellation of 4 terms. Oh, 15x. We've seen that before. And then we've got to make this turn into 125, and it's always a positive at the end. That's always positive. And that's just effort on your part to learn how to do that. You just have to know the cubes, 8, 27, 64, 125. Basically, that'll take care of you. All right, SATs and achievement tests and all that stuff. You know those numbers. You're going to be able to work with cubics. All right, so that's that one. Number 5. I think I'll start changing that as we go along. 2a squared plus 5a minus 12. Oh, I see a little addition and subtraction. I think I'll convert it into multiplication. I'm going to try. I got the marker. I think I can make that happen. Yes, I did. Now I got to figure out the factors of 12, because whatever they are, they're going to get doubled here. They're going to get doubled. So if I have a 1 and 12, and I'm not seeing 5. 4 and 3, 4 and 3, I'm not seeing 5. 6 and 4, I'm not seeing it yet. 4 and 3, there it is. 4 and 3, 8 and 3 can become 5 if I take 3 away from the 8. Okay, so your brain has to just, try the different combinations. There is a way to show some, larger trinomials by factor by grouping. We'll do a little factor by grouping, but not in this context. We got more important things to do. All right. Okay, so that's kind of it for factoring. Square root of 48. Square roots. 4, 9, 16, 25, 36, etc. Bingo. 16 goes into 48. So this could have been the square root of 16 times the square root of 3, which is 4 root 3. Now, let's say you didn't see that. Let's say you didn't know that 16 went in. Then you'd have to maybe take a 2 out. Oh, that would be the square root of 24. Oh, well, I guess maybe you take another 2 out. That's the square root of 12. Then maybe you see the square root of 2, square root of 2, square root of 4, square root of 3. And hopefully you see that is 2 times 2 times root 3 is another way to get 4 root 3. And that method is helpful in the next problem, number 6. Oh, number 7, I must have missed something somewhere. Number 7, square root of 6, 2 root 3 plus root 2. When you get good at these, you just write your answer. But right now, let's look at 2 root 3, 2 root 3 plus root 2. And let's see what that becomes. Well, I see that times that. I think that's the number 3 times 2 is 6 root 2. And over here, I can see a root 2 times a root 2. Let's get that out of there. I can see that is 2 times root 3 and its addition. Now, this is like saying 6x plus 2y. These are not connected. I mean, they could be. We could say X is 3 and Y is 3, and they'd be the same number. We could count threes, but we don't know what those are. So you can't have them. That's your answer. Okay. Let's look at the square root of 12. A squared b to the 11th. And that's the same thing as 12 a squared b to the 11th to the 1/2. Okay, but we'll work with the square root of 12. Square root of 4 times square root of 3. Oh yeah, I know the square root of 4 is 2. And I'm going to ask you to memorize the square root of 3. It's very important. Okay, it's extremely important to have a feeling for size. 1.73. I'll give you a little handout in a little while with some very useful numbers to know. There'll be some students in this class that won't be able to answer that by the end of the semester, if you're like every other class I've had. But maybe now that I've said that, I don't know if I've ever said it at this stage of the term, maybe you'll make it. Maybe everybody will know that. We'll find out. All right, so rules of exponent multiplication. So really dividing these exponents by 2. Whatever goes in evenly comes out, and whatever has a remainder stays in. So wait a minute, I forgot A. So A and then B to the 2 into 11 5 times, remainder of 1. And that should be regardless, whatever numbers we give for A and B. That's the simplified version of that problem. All right. And while we're at it, no reason I can't introduce cubics. It's the same process. 24, A3, B12, C17. We already started talking about if something's a perfect cube, means 3 fits in. It's a multiple. The exponent's a multiple of 3. So we got a couple of perfect cubes here. Question is, what numbers fit in? Well, 8 does, right? So what's the cube root of 8? Cube root of 8 is 2. So I can take a 2 out. Don't forget to write the 3 here, or it's a mistake. Without the 3, it's a square root. And we use square roots so much, we don't write the 2. It's just understood. But this is a cube root. And so 8 goes into 24 3 times. So on a calculator, the cube root of 24 is exactly equal to 2 times the cube root of 3. The benefit of this is, well, actually there isn't one. I know the square root of 3. I was about to say, what's the cube root of 3? I don't know. Maybe some ancient mathematicians. Well, then if they were friends of mine, I don't think they knew either back then. Pythagoras and all this. Oh no, Beard, but no, I'm not that getting there. All right. So a perfect cube. 3 into 3. Another perfect cube. Yes. B to the 4th 3 times. Yes, that's a perfect cube. That's b to the 4th times b to the 4th, length, width, height, b to the 4th. Yeah. So therefore 3 goes into 12 4 times. 3 goes into 17 5 times with a remainder of 2. All right, so that one's done. Let's see. Okay, so now we got linear 8 negative 2. All right, well, we can quickly write x minus 8 minus 2. I'm not even going to write y equals anymore. And then we're going to 8. Oh, the old guy threw a curveball at you. Looks like we better plot this. 8 negative 2 and 8 negative 23. We got to figure out what to call this thing. 8 negative 2, 8 negative 23. I got a feeling even 8 negative 15's on here. I got a feeling 8 7 is on here. I wonder what a good name for this would be. Well, how about x equals 8? All right. Next. Quadratic. Negative 1. So I'll write x plus 1. Yep, that's the smallest. When I drop that in there, that's no area. And squares generally 1, 4, 9, right? Same thing, symmetric in this direction, but it seems like 0. 0 times 0 is a minimum. And, you know, if I put a negative in front of that, I get a maximum, but I don't know what my next values are, so I better look at the board over here, 30. So a -1 gets me 30. Well, I just made that happen. Yeah, you drop -1 in, you get 30. Now, when you drop a 5 in, you get 36 plus 30. Yeah, that's what you get when you drop a 5 in there. And we want minus 23. Well, geez, 36 doesn't work. Get rid of that. How do I get from 30 to minus 23? I think I gotta go down 53. That's not quite negative doubling of the quadratic process, the rectangular relationships. All right, so that's that one. I should have written 523 up there. You can go back. You can go back and do that again if you need to. Square root. -2, 7. No, I think I can start with x plus 2 plus 7 for the same reason. Square roots have a smallest distance, right? I can make that square smaller and smaller and smaller. And that distance going to be 0. So I want the square root of 0. But if I'm starting with that number, I want it to act like a 0. I got to make that statement. And now I'm going to drop another number in. What am I going to drop? Oh, CD. Ooh, CD. OCD. No, good thing there's not an O in front of that. But anyway, I'll drop a C in. And that gets me the square root of C plus 2 plus 7. And I want that to equal D. I don't see the letter D over here at all. Thinks I got to get rid of just about everything there and just write D. Well, how do I get rid of this? Oh, I can get rid of that with this. C plus D, that, or 2, that's a 2, excuse me. Got D in my mind. Now I got ink on the floor. There we go, it came off. I'll get it a little better later. So it's C plus 2. Okay, well, that gets rid of that. I don't see the number 7 over there, so I guess I got to get rid of the 7 and bring in the D. Yeah, I guess that was a good job of getting rid of what I didn't want and bringing in what I did. That's all about conversion. Yeah, that's what it is, all right. Starting to sound like a Gillbilly. Okay, 0, 0. I'll look at it graphically. 0, 0, -8, a positive 8, -3, positive 8, -3. Boom. Ooh, absolute value. I think I want to highlight 0, 0. Yes, I just did. All right, and I want it to go through 8, -3, so 8 doesn't work. -3 does. I think that does it. Oops. Right. So what I didn't do was I didn't write things that I didn't need to write. Yeah, 0 is so important in math. Yeah. What have I got there? Y minus 5. Seems like I skipped some problems over there. Name 3 points. Maybe that's what this was. Yeah, this must be name 3 points on the line. Y minus 5 equals -3/10. I hope I'm doing the right thing here. X minus 1. Just going to keep moving along. All right, so what do I see? I see dyslexic X to Y. I think it would be X's to Y's in that direction. So 1 makes a 0. 5 makes a 0 over here. So my X 1, my Y 5, and then rate, linear rate, constant rate of change from one place to the next, that ratio of change. So I'm going to go down 3 with the Y's, 2, -1, -4, etc. You go up 10 with the X's, 11, 21. And if I'm on a test, I'm going to make sure 21, -1 works. So I'm going to put 21 in, I'm going to put -1 in, and I'll do the problem out very quickly. 21 minus 1 is 20. Oh, that's nice. 10 goes into 20 twice. That's nice. -3 times 2 is -6. And -1 minus 5 is -6. I don't have to ask the teacher if I did it right. I did. 3x minus 4. At this stage, you should be squaring these binomials pretty quickly with the pattern. If you haven't looked at the pattern by now, I suggest you get with it. Everybody can make a careless mistake, but that conversation should be meaningful to you right now. But if it isn't, please take the time to do this out until you get there. Yeah. Right. 11 x cubed minus 3y5 squared. I just wanted you to know that that's 121. 11 times 11. Probably should know that coming out of grade school, but some people don't. X cubed squared, x to the 6th, right? X cubed is x cubed squared is x cubed times x cubed, which is x. 3 of them times 3 of them, 6 of them. All right. Double the product. Minus 66 x cubed y5. We don't know what those numbers are, but I know how many of them I got. Right? And then squaring, always positive, 9y to the 10. Hopefully you're doing those more quickly and easily each time. All right, 12. So I'm going to sketch 12. 1/2 t minus 1900 over 23 plus 100 equals y. My outputs, inputs to outputs. So this is G of t on your sheet. All right, time. So in the year 1900, we've got a certain amount that's growing. Oh, decaying, excuse me. We got something that's decaying. So I'm going to come in with the shape immediately. Now, what's decaying? Height of 12, but it's on top of 100. It's 12. And if I'm cutting it in half, it's 6. It's 3. That's not too bad a drawing. All right, so the question is, what do I want? Well, I like 1/2 to the 0, and I like 1/2 to the 1. I know those answers. 1/2 to the 0 is 1, and when you multiply something times 1, you don't need a calculator. And 1/2 to the 0 is a multiplication times a half, which isn't too bad. That's not too bad. Some of you might even like 1/2 to the 2. And then you're taking 1/4 of something. Right? But I like 0s and 1s. So I'm going to pick 1900. And that should get me a jump of 12. 1900 minus 1900, 0 divided by 23 is 0. What is 1/2 to the 0? It is indeed 1. So I got one jump of 12 on top of 100. Yippee. All right, and then I'm going to pick the number 1923. And I hope you can see that when I put it in, I get 1/2 to the 1. And 1/2 to the 1's a half of 12, 6. So 1923 gets me 106. And 1900 gets me 112. Okay, then I want the inverse of this. Well, we're going to get the inverse 2 different ways. First, we're just going to draw the inverse. And I've got it right here. The inverse of y equals 100. The inverse of a horizontal line is a vertical, which we just talked about earlier in the sheet. All right, and I know that 1900 gets me 112. That's my x to my y. Well, the inverse is the y back to the x. So, you know, I get 112. Oh, did you notice that that's 12 units in that direction? Interesting. Yeah. Instead of 12 units vertical change, yeah, must be a coincidence. All right, 112, 1900. Put a little dot there. And 1 106. 106, 106, 106 is actually closer than 112. Wow, 106, that's 12. Oh, that's only 6 units from 100. 612. Well, that's something strange going on here. I think I got to move this one over so you can see it a little better. 112, and that occurred at 1900. And 106 got me 1923, which is a Y value that's bigger. Okay, and looks like I've got that shape. You probably need a third point to prove that to yourself at this stage, but here's a little display. Let's see, you were looking at exponential decay, I believe. Yes, and I'm going to switch the X's and the Y's. The Y's are vertical, I'm going to make them horizontal. Yeah, let's see, we got decay. Well, that's, I'm looking backwards here. That's awkward for me. All right. And then we're going to switch to the X's and the Y's. Oh, yeah. All right. So something going on there. Now, we could always talk about exponential growth. That's exponential growth, switching the X's and the Y's. I don't think that's what I wanted to see. Oh, yeah, it is. I'm looking so upside down. Shoot, whatever. I'll do it in class and spend a little more time with it. So what was the equation? Well, there's 2 ways to get the equation. The inverse. One is to build it off of what you see. What do I see? I see Y equals 1923. How do I get from 1923 to 1900? I'm subtracting 23. And then it's a logarithm. And I'm looking at exponential values here. You know, and I see 100, so I'm going to write X minus 100. Yeah, to highlight the line of demarcation here. All of my values for X are bigger. And which one? 106 is 6 units bigger. Yep. And then when I drop in 112, I get 12.6, which is 2. Now you say, well, you know, the other one was something to the 1/2 to the X. But these are exponents with a negative sign in front of them, which means that I can make it a positive and take the reciprocal. Okay. Now, we had originally, my Y was 12, 1/2, X to the 1900 over 23 plus 100. So let's build it symbolically. Addition of 100 becomes subtraction of 100. Oh yeah, I see it over there. Okay. Oh, multiplication by 12 becomes division by 12. Okay. Yeah, remember, we're going to get to this in a second. There's going to be a reciprocation here, I'm sure. And it's a logarithm. All right. Base what? Base 1/2. That's the inverse of addition of 100, subtraction, the inverse of multiplication, division. The inverse of 1/2 to the is log base 1/2 of the. Hope I said that right. That's awkward for you, you know, but that's what it is. That's what we got to look at. All right, so we're here. Now I've got division by 23, so I got to bring in some multiplication. And I got subtraction of 1900. I got to add 1900. So it's a little bit different. A little bit different, but I got the 23. Oh, wait a minute. I got something that maybe I made a mistake with somewhere. 1923 and 23. So I'm probably over here. I said something wrong right there. Okay, so let's start with, oh, okay. Usually I start with the first Y I see, but let's start here. 1900 to get to 1923, 23 units. Okay, X minus 100. We'll start with 112. we put 112 in, then this is 12. Okay, I'm learning something here about it's breaking a rule. I usually go from left to right, but I think it might be better at this stage to go from right to left. So when we drop in 106, I get the 1/2. All right, so probably should have started with an exponential growth problem to avoid this minus and this reciprocation, which is, I don't know how many people would see that even, so. Probably should have started with exponential growth. But it is what it is. It's not wrong. So it was worthwhile to see. And then we've got, boy, this is taking a while. Longer than I hope. Yeah, so the inverse of that we just covered, and we want to know when G of t equals 124. So let's go back to G of t. G of t equals, I think I'm getting this memorized, t minus 1900 over 23, and we've got plus 100. And we want this to equal 124. So what am I going to do? I'm going to subtract 100, 24. I'm going to divide by 12, which is 2. I'm going to do the inverse. Log base 2 of, log base 1/2 of 2. That's equal to -1. -1 times 23 is minus 23. And if I add 1900 to that, I get 1877. And if you remember, this was 12 units here, and that got me a height of 112. 124 is over here, and it was 1900 that kicked out that, right? So if this is a timeline, adding 24 to 100 happened 23 years earlier. Okay, so that's what was going on there. All right, 125 to the 1/2. I'll try to do this more quickly. 125 to the 1/2. It's only there to figure out if you knew that meant the square root of 1 over 25, which is 1/5. 1/5. Why? Because 1/5 times 1/5 is 1 over 25. So the square root of that is that. Okay. Log 27, get 1 over 81. Log 27 to get 1 over 81. Got to get the same base. So I'm going to call 27 3 cubed. I'm going to call 81 3 to the -4. Okay, so what's my answer? I got to get rid of the cubing, and I have to bring in the power that I want. Right? Why? Why can I say that? Because 3 to the 3x, remember I'm putting an x there, equals 3 to the -4. 3x equals -4, so -4/3. All right, so we'll go back now and see if it works. 27 to get 1 over 81. All right, so the cube root of 27, cube root of 27 is 3. 81 is 3 to the 4. 1 over 3 to the 4 is same as 3 to the -4. Oh yeah, same base, same base. There's the exponential activity. Language matters. All right. Log base 9 of 1. Just basically asking the question. I hope you're hitting the space bar each time. I hope you just know the exponent you put on top of the 9 to get a 1 is 0. Okay, log 0.01. All right, so well, first thing you should do is count tenths, hundreds, thousands, 10,000s. That's 1 over 10,000. Well, I can do scientific notation here. That's 10 to the 4th. Oh, that's the same thing as 10 to the -4. And this is base 10. So the answer is -4. But we don't have to write it. We're supposed to know it. All right, log 3. -9. Space bar, think about it. I just keep going. Hey, this is all about 3 to the x. 3 to the x is tripling function. Right? 3 to the -1 is a third. That's still positive. That's still bigger than 0. 3 to the negative 2. Well, it's 1/9. That's still positive. Yeah, I don't think that you can put anything on top of 3. 3 to the 0 is 1. That's positive. I don't think you can put anything on top of 3 to get a negative. Slash it. Good. We're going to slash it from now on. We're not going to talk about no solution. We're just going to slash it. Good. All right, next problem. 25. 3 and a 7. X is 3, Y is 7. Then what's Z? 49 and 9, 58, square root of 58. Let's check it out. 2 times 29. Nah, can't simplify that. Square root of 58, which is a little less than 8 units. Square root of 64 is 8. All right, minus 2/3 X. Plus 8. Boy, we've grabbed this a couple of times. Minus 2/3 X plus 8. Linear function going down. Running out of ink here. 5x plus 2. 5 halves x plus 2. So plus 2 might be there. Up 5 over 2. I got an x-intercept around 1 unit. Let's find it. I don't like fractions. I don't like division by 2 and division by 3. I'm going to multiply this thing by 6. Negative 4x plus 48 equals 15x plus 12. Well, it's not so bad. 19x. Keep your division positive. Take 12 away, 36. So 36 divided by 19 equals x. My answer was a guess of 1. It's closer to 2. I'm fine with it. Okay, 27. Oh, I mixed up some numbers here. Minus 2, 1 to 5, 4. You know, how far is it from negative 2 to 5, 7 units? How far is it from 1 to 4, 3? There's my square root of 58. Must have been Freudian. It's that distance. Roots. Minus 2. X plus 3 squared. I don't care what numbers you throw at me. There's a pattern here. So roots. So I got negative 3 plus or minus the square root of 10. You go figure out how I did it. No, I'm a kid being sarcastic. Set it to 0. Well, addition of 20, subtraction of 20, multiplication by negative 2, division by negative 2, x squared equals some number. There's a positive and a negative. So if I'm undoing squaring, I got to have the positive and the negative, root 10. And positive 3 becomes negative 3. That's how I got that answer quickly before. So it looks like if you got the root, if you got the vertex and you got the A term, you got the roots in 5 seconds or less. All right, sketch. Minus 2x squared minus 12x plus 55. All right, I know it's cup shaped down. And I know 0 gets me positive 55, and that's on this side. So I know my x is negative, but minus b over 2a. Yep. Negative 3. I'm going to put negative 3 in. And if I put it there, I get 36 cut in half is 18 plus 55, 73. I'll check that real quick. 73 to 55 is 73 to 57 is 22. I don't like that number. Maybe I made a mistake. Negative 3 times negative 12, 36 cut in half is 18 plus 55, 73. Okay. 5, 15, 18. Okay, so it's just, so I went down 18. And if I look at the square change from negative 3 to 0, it's 9. Negative 18 divided by 9, negative 2. If I'm on a final exam, I'm moving on. That's correct. All right. Brain got a little slow there. So we got a log. Base m to the 7th. Yeah. I guess I'm asking, what do I have to do exponentially to make what happens in terms of m happen? All right, so I'm going to manipulate this as we go through it. God, I hope that's got a little glare on the screen. Yeah. I'll try to work to the side a little bit. Well, it doesn't work. Oh, well, I hope that this video came out okay, because I'm not doing it again. All right, so back to this problem. I'm gonna switch the M's. I'm gonna put the 1 on the top as a positive and the 4 on the bottom as a negative. Oh, that sure looks like 1 over M to the 3. Looks like 1 over M to the 3. I'm gonna flip it, which makes it M to the 3. And did it flip? And now it's M to the 15. So I got to make this happen. I want the 15th power, not the 7th. So let's get rid of it. Let's get rid of the 7th with the 7th root. And let's bring in the 15. That's your answer. You might have to play that again. All right, vertex for 5x squared minus 20x minus 3. What's the shortcut? Minus b over 2a. 2. Okay. 2 goes into minus 20 minus 40. I can cut that in half and subtract 3 and get minus 23. Now, why have I been cutting it in half? Well, let's put a 2 in here. That's 20. You tell me what 20 minus 40 is. Seems like it's half of minus 40. That happens every time if you have the correct number, minus b over 2a. Geometric reasons for that, which we'll explore later, not right now. Oh, I got another one here. 5, a to the 0. Looks like the marker is going to hold up. 3, a to the minus 2, b to the 9, all to the negative 2. So I've gotten in the habit of simplifying the parentheses first. So 5/3 doesn't change. Minus 2 goes up to the top. A to the 0 is 1. So I've got a squared. One of the b's can be canceled. So that's b to the 8 in the denominator. 1 minus 9, negative 8, which is 8 in the denominator. Okay, now I can flip it. I'll flip it. If I flip it, I'll work over here. No, that's going into the stay on this side over here. So let's flip it. Let's go with 3b to the 8 over 5a squared. And now let's square it and let's get our final answer. 9b to the 16 over 25 a to the 4. Okay, come on, marker. Almost done. We're going to sketch an exponential growth problem, a tripling function. We're going to sketch 5, 3, x minus 8 over 9 plus 2. I'm a big fan of 3 to the 0, and I'm a big fan of 3 to the 1. So I'm going to let x minus 8 over 9 equals 0, and I can see x equals 8 is very friendly. I'm going to use 8. Then I want to get the number 1. So I want x minus 8 over 9 to equal 1. So I want x minus 8 to equal 9. I guess x equals 17 is a very friendly. And all I need is 2 points because I know the general shape of exponential growth. I put an 8 in, I get 3 to the 0, 5 times 3 to the 0 plus 2. My brain can work for that. That's 1, 5, 7. So I really just jumped 5 on top of 2 to get 7. And it took the number 8. And if I want 3 to the 1, that means this is going to triple in size. It's going to be a jump of 15. Provided I use the proper number, which I think is 17. 17 minus 8 is 9. 9 divided by 9 is 1. Yep, I got 15 plus 2 is 17. And that happens. 17 gets me 17 by coincidence. That's sketched. Okay. So maybe it's time to see if you can name a tune. Let's say that y equals 6. it's time to try one. Let's say that in 1903, a very good year. I remember it well, 1903. There were 40 sheep in Gill. There have always been at least 6 sheep in Gill, but our population has gotten really good now. Population of sheep is, oh God, it's so much bigger now, 200. Yeah, we got 200 sheep. So what's this equation? Well, I think we want to start with 6. And all this growth is above 6, and we got to get to 40. So I guess that's 34 to get the first calculation. I don't think it's going to work out for the second one. I don't think adding 34 is going to take me to 200. So we'll get rid of that one. The next time I better make some room for the exponential part, but it's the end of the video. I'm going to just keep going. And I want to get from 6 to 200. That's 194. That's about 5. I'm quintupling. Yeah, it's more than 5 to the x. This is bigger than 5 to the x. Oh, I got to put a 1903 in there. So x minus 1903. And I got to look at the elapsed time from 1903 to 2023, I believe is 120 years. Yep, that's that equation. All right, and now I want a parallel line through esoteric. Small group knows what I'm talking about here. And vacuous. Oh, that was stupid of me to put EV. That's my sister's initials. Oh, sorry, Ellen. Oh, anyway, 5x plus 3y equals whatever, 59. I don't care, some number. All right. And we want to look at the interplay between the change in x and the change in y, which is going to be 5 over 3. Right. And so I want the same slope, 5 over 3, and I want EV, esoteric, x minus e gets me v, and that's parallel, and I'm out of ink. I'm going to end this. Oh my God, I feel like I've been talking for an hour, but good practice. And we want you to have a good foundation in this discipline going forward. See you tomorrow.